Okay, let's talk about circles. The most interesting shape in the universe. Uh-oh. Oh no. Oh no. Circles. And specifically, when we talk about circles, we're not just talking about the shape. We're talking about centripetal force. So let's quickly look at this word centripetal. Centre. I don't know if that's French or not. I just said it with a strange French accent. But this refers to center. And pedal, this means seeking. Okay? There's your like dead languages lesson for today. So center seeking force. So what does that mean? We probably all grew up saying the word like centrifugal force at some time or another. But we're gonna like sort out what all of this stuff means. So the first thing I want to talk about is just a quick reminder. Okay, a force is a push or a pull. So we've got a center seeking push or pull. And I think where we'll start is let's imagine that we are looking at some object that's traveling along. Let's say it's a bowling ball, because why not? So here's a bowling ball, and this bowling ball is zipping along here, like that, with some velocity. Okay. Now, if zero forces act on this bowling ball, what will it do? Right, it'll continue at the same speed in the same direction forever and ever, and this is what Newton called inertia, right? The tendency for some mass, m, in this case a bowling ball, to make sure we all know it's a bowling ball, the international bowling ball symbol needs to be put on it, right there. Okay, so there it is, bowling ball. And if you want to change something about this motion, you're going to have to apply a net force. F net equals ma, right? Now, so far, we've really only talked about what happens if we apply a force like this. Well, it speeds up. Or if we apply a net force like this, right, it will slow down, okay? But what if, instead of this thing just traveling along in a straight line, what if we want it to do this? What if we want it to deviate from the straight path and begin to go into a circular path? Okay? How could we make a bowling ball that's traveling along like this change direction and start to follow this path? Well, what are some ways that we could make this happen? Could we push on it? And how would we have to push on it to make it follow this path? Absolutely. We'd have to push on it like here, if we were here. The bowling ball's over here. We'd have to kind of push like this, right? We always got to be pushing kind of perpendicular to the path of the ball, right? So if we think about it, we're always forcing this ball to aim towards the center, right? Here's these blue lines here are representing its velocity vector as a tangent to the line that's on. This one doesn't look quite tangent. And what you'll notice is that the force required to make it turn is always at 90 degrees to the direction that the ball is currently traveling. Okay, so we were 90 degrees here and 90 degrees here. So if we want a ball traveling along straight to go in a curved path, we need to push or pull it towards the center. So what are some ways we could do this? Wind. Why not? Okay? Wind could do this if the wind were in the right direction. This is the international like symbol for wind. Let me fix his eyes. Yeah, there we go. See the old angry cloud. Yes, wind could do it. What else could do it? Could a string do it? So we could attach a string to the center of this arc, right? So we tie a string to the bowling ball, And then it's a tension force that's causing it to go in a circle. So tension force, wind force. We could build like a curved wall here, couldn't we? We could build like a curved wall. And then it would be like a normal force that's pushing it towards the center, right? Or let's say the ball, for some reason, has a positive charge. We could put something negative at the center, and just that force of attraction could make it go around. Or let's say this is a planet and this is the sun, okay? A planet could go around the sun in a circular path. Now we've got the force of gravity causing it to go in a circle, okay? So any force that starts to cause a mass to go in a circle has a special name, and that is centripetal or center seeking. Centripetal force, okay? It is a real force that must be applied to an object with mass to make it change directions, specifically to circle around some kind of central attractor, all right? Whether that is done by tension, by pushing, by a normal force, by electrostatic force, by gravity, by magnetism, you name it, okay? All of these things can be considered a centripetal force. The actual nature of it is sort of irrelevant. The same math will work whether it's tension or whether it's electrostatic or whatever it happens to be. Okay, so just to continue here, if we're supplying a force, right? If we're supplying a force at 90 degrees to the velocity, will the velocity change? No, it will not. So, well, that's actually, we got to be careful. Because remember that velocity has two components, right? It has a magnitude. The magnitude is the size of the velocity. But it also has a direction, okay? The magnitude will not change if we're applying a force at 90 degrees, but the direction will change. You see here? This is velocity here. The velocity is the same magnitude here, but its direction has changed, okay? So technically, the velocity does change, and I should make all these the same height, but it's not the magnitude anymore, it's now the direction that's changing. And I'm just gonna write that down, okay? So a centripetal force acts at 90 degrees to the velocity vector. Okay. This results in a direction change, but not a magnitude change. We're used to dealing with mainly magnitude changes. Although I guess when something goes from positive to negative, that was a direction change, but... All right, let's talk about an object moving in a circle now. So let's put an object on here. That is not an object. So there it is. Some object with a mass. Okay. Put a center on the circle. And we'll say that at some point in time, the object is traveling along here. And let me just make this look a little bit better than it does. Okay, so a couple things I want you to notice. One is that the velocity at any given moment in time is a tangent to the path of the object moving in a circle. Okay, so this is the velocity, and the velocity is tangent to the circle. Okay, we're going to call this point A. All right, now sometime later, the same object is going to be found, say, over here. Okay, so it's moved over here. We're going to keep the same magnitude of velocity, but we're going to change the direction of travel of that thing, and we're going to indicate the value of it. Okay, by drawing a tangent line. Okay, so here's our velocity at the point later in time. Okay, so let's write in here that we've got t1 over here. Let's call this point B, and we'll call this at time 2. So between time 1 and time 2, we've had a change in velocity, right? Not the magnitude, but the direction. Okay? So what we want to talk about is if we've had a change in velocity during a change in time, we must have had an acceleration, right? So from the old days, we know this. Acceleration is a change in velocity happening during a period of time or a time interval. So what we're going to get here is acceleration equals, and let's just distinguish these two things, v2 and v1. A equals v2 minus v1 over t2 minus t1. Okay? Well, this is a bit of a problem, right? The way I've done this, if we just put numbers in here, we're going to get 0 on top because the magnitude has not changed. But we have a way of subtracting vectors, right, that we learned earlier, okay? And that's to do it graphically. So let's take these two vectors and see what we can do with them. So what we want is v2 minus v1. So we want to actually take this guy, I'm going to copy him, move him over here, okay, and this guy, move him over here. And we want to say here, oh, why did that change color? Don't do that. Huh, that's weird. Okay, come on now. It doesn't really matter if it's a different color. v2 minus v1. Well, if we're talking about subtracting vectors, how do we actually deal with subtracting vectors? We do what with them? Yeah, you add the opposite vector. So it's like saying v2 minus the reverse of v1, okay? So v2 minus v1. So what we're going to actually do is we're going to take this guy again, okay? And we're going to flip him over. Look, I have a flip function. Flip left to right. Did it work? Heck yeah, it did. Okay? Now we're going to add them tip to tail, right? Add the opposite. So we get this happening. And now we have a resultant vector, don't we? We have a resultant vector. So let's draw that resultant vector in here. Okay? Let's make it a different color. Let's make it like gray. Please let me make it gray. There it is. So there's our resultant vector. When we take the change in velocity, we end up with this little thing here. And I want to show you what I can do with this. So just give me a sec. Okay, so if we take this, we just move it. What we should find, right, if we put it halfway between these two, we'll see that the average change in velocity aims towards the center, okay? So the change in velocity for time is an acceleration, right? So in other words, what we're saying here with this little exercise is that the acceleration of this object is towards the center. This should make sense since we had to apply a centripetal force to it, right? So if we subtract v2 minus v1 for the given time, we end up with an acceleration here towards the center. So I'm just going to draw that in. And the reason I'm doing this is because before we talk about how we get the formulas to deal with centripetal force, we need to talk about centripetal acceleration. So my centripetal acceleration, AC, points to the center between any two given velocities as the velocity is changing. If I would have made this smaller, we would have got a more vertical one, but it would have been back up in here and still would have pointed towards the center. So no matter where I go, okay, I will always have an acceleration towards the center, and that's because in order to go in a circle to begin with, I got to apply a centripetal force. Okay. All right, so let's work a couple things out here. So I want to relate a few things together here. So what we're going to do is we're going to draw in a couple of radii here, right? So these are radii that extend from our mass at different points to the center, okay? And this I'm just gonna get rid of you for a minute, okay? And okay, and so what we're also going to do here is we're going to draw in a little theta symbol here, okay? And we're also going to draw in a chord, okay? So here is a chord. Do you guys know what a chord is? This is the arc, and this is the chord. Yes, it is that as well. Now it turns out that actually what you get is, you get that this, which probably should make sense, and this become similar triangles, okay? So what that means is we can set this up. Now, delta V, right, that's this guy here, delta V divided by one of its sides, so we'll go by V1, or any V really, but by V, should give you the same thing as chord AB over R, okay? Chord AB over R. Okay, so the ratio of sides on similar triangles are the same, right? Similar sides, the ratio of similar sides should give you the same value. Do you agree with me? Okay, so this is chord AB right here, okay? This is chord AB, and this is delta V, and they are corresponding sides of this triangle. These theta values are the same. And you're going to have to trust me on that. I don't really want to go through all the geometry to prove that that's true. So now what I want you guys to imagine, okay, is what would happen if we decrease the amount of time that this happened over, okay? So can you look at this? If we decrease the amount of time, it's like we're moving B closer and closer and closer to A, right? Smaller and smaller amounts of time. You'll notice that what happens to the length of the chord versus the length of the arc as we decrease time. They're going to approach each other, okay, in terms of how of their distance, right? So I'm just going to write this down. So something to note, because it's sort of important, and what we're going to do sort of relies on this. As the span between T1 and T2 decreases, so the shorter and the shorter the period of time that the travel happens, the closer in size, or length, I guess, in length is probably a better value, in length, chord AB approaches arc AB, okay, in terms of length. Let's just double check that. Now that's kind of like a brushing up on calculus idea, but the length of chord AB and the length of arc AB essentially become the same if the period of time between these two things decreases enough. Are you with me? So what that means then is that if we're to start calculating distances here, what we could say is we could say velocity times time should equal the distance between A, B over a short enough period of time, okay? This is the way it actually travels, but since we're dealing with similar triangles, we have to talk about chord AB, but it would be true to say that over a small period of time, the distance traveled along the arc is the same as the distance traveled along the chord for a given amount of time, okay? Okay, so now what I want to say is that we could say that if the time frame is small enough, okay, this distance of chord AB, okay, is equal to arc AB. Now we talked about that already. But let's change this then. So let's say then that delta V over V should be equal to velocity times time, or times change in time. Okay, velocity times change in time should be equal to chord AB, and therefore also equal to arc AB if time is small enough, divided by r. Okay, I know that's probably a little bit to digest, but this value is meant to represent distance from A to B. Okay, distance from A to B is velocity you're traveling at times time. Now we've got velocities like all over the place here. So we're going to do a couple things in just a minute. Now it's algebra time. Okay, so job number one for algebra is to, let's rearrange this so it now looks like this. Delta V equals V squared delta T over R. Because I took V and I multiplied it by V, right? So V squared. Now I'm going to divide T off of here, so we'll get this. Delta V over T equals V squared over R. And now look what we just went and did. Delta V over T is the same as, good. And what we've just done is derive the formula for centripetal acceleration. Okay? Now, while we're on a roll here, I want you to just recall something. Recall, F equals ma. Okay? So, watch this madness. Let's take mass and let's multiply it by, what am I doing here? How do I undo? I forget already. Let's take this and let's multiply everything by mass. So what do we get? We get m AC equals mv squared over r. And we say m times a is the same as force. It's centripetal force, so we put a subunit of c on there just so we know. Equals mv squared over r. We did it. We derived a formula for centripetal force and centripetal acceleration. Now these are part of your arsenal. Oh yeah. So let's do a question. A problem. So let's solve a problem using this stuff, okay? A mass of 3 kilograms is whirled around on a 70 centimeter long string such that it moves at 12 meters per second. So let's draw a picture of this. So here's the center. Yeah, here's the center. Here's the string or cable or whatever you want. Here's a 3 kilogram mass. And it's the magnitude of its velocity is 12 meters per second. Okay. Just messing with you. Yeah. Does not change the math. Okay. And we got 70 centimeters here, which we'll have to change into meters, so that's pretty easy. 0.7 meters. And you want to find the tension in the cable. Okay. Now here's the thing that you might notice. It does not anywhere in here say the words centripetal force. It says find the tension. You are expected to understand that this is one flavor of centripetal force problem. One where it's going in a circle because of a tension. Tension, of course, is in the cable and will always be pointing towards the center, okay? So this is a straightforward application of the formula we just derived. So FC equals mv squared over r, 3 kilograms, 12 meters per second. Oops. Why did I do that? 12 meters per second squared divided by r, 0.7 meters. So I get 617 newtons. Okay? Now just a couple of things to think about. Which one of these factors is going to affect centripetal force the most? Going to be velocity, right? It acts at a square. What happens if I keep the same velocity, all right? Keep the same velocity, but I decrease the value of r. As r shrinks, what happens to FC? Right. If I make this shorter and shorter and shorter, I'm going to require a larger and larger force to keep it turning, okay? And then mass is linearly proportional to the force. So if I double mass, I double force as long as everything else stays the same. It's important to kind of think about that. If r gets larger, the amount of force needed to keep it going at 12 meters per second is much less, okay? Are you with me?